morning. So, today we will still continue with some of the aspects of our xanthine oxidase and other related oxidoreductases. So, as we are just looking at the xanthine oxidase, which is operating on hypoxanthine, xanthine and ultimately producing uric acid. So, if we consider, as already we discussed earlier, that all these three molecules are different from the basic point of view that their skeletons are all same. Only thing that is hypoxanthine has one oxygen atom attached to this particular carbon on this 6-membered heterocyclic 2 nitrogen bearing ring, whereas xanthine has 2 oxygen atoms and uric acid has 3 oxygen atoms attached to this carbon, the second one, and ultimately between these 2 nitrogen this carbon. So, if we consider that the transformation mediated by this molybdenum bearing enzyme xanthine oxidase is taking place from the conversion of hypoxanthine to xanthine and then xanthine to uric acid, which is deadly for the living system and also for the human being. That accumulation of uric acid in the blood as well as in the body has some severe consequences afterwards, because this particular species compared to hypoxanthine and xanthine is much soluble in water and it can crystallize from aqueous medium depending upon the pH of that particular medium. So, crystals of uric acids are also forming in some of these cases. So, basically we will just focus our attention on this particular conversion, because the conversion of this xanthine to uric acid is really very important to study, because this hydroxylation reaction and that oxygen atom transfer reaction is taking place on this particular carbon. So, the positioning of these carbon when we go from hypoxanthine to xanthine, that means the insertion of the oxygen atom on this carbon is little bit different, getting xanthine from hypoxanthine compared to that oxygen insertion for the last step, where we get the uric acid bearing 3 oxygen atoms, that means this particular carbon center. And all these cases, the basic aspect what we can see is that since we are talking about a molybdenum bearing enzyme, so molybdenum oxo species, if in the intermediate is forming, and which we have seen earlier that it can be transferred from a non-oxo molybdenum center species to a oxo molybdenum and then ultimately to a dioxo molybdenum species, that this oxygen atom is getting activated due to the coordination to the molybdenum center, and ultimately that oxygen is transferred to hypoxanthine to form xanthine and ultimately to hypoxanthine to uric acid. So, it is the activated molybdenum enzyme where we have the molybdenum oxo form is present, that is utilized for the hydroxylation reaction on this particular carbon of xanthine. And this particular hydroxylation reaction is little bit different from the conventional other type of hydroxylation reaction based on other metal ions like iron, copper, etc. are little bit different, because in this particular case where xanthine is also a very good heterocycle, and if we consider that this particular molecule having 4 nitrogen bearing centers, only this is the nitrogen which do not have any hydrogen attached to it. So, its coordinating ability is much more. So, this particular nitrogen can go and bind to the molybdenum center very easily. So, the substrate, if we consider that this xanthine is the substrate, so substrate can go very nicely on the molybdenum center, and that molybdenum center bearing the oxygen atom, that means the molybdenum oxo site, that oxo group if it is possible to transfer on this carbon where this carbon is in close vicinity of the molybdenum site, we get the typical hydroxylation reaction. So, in a big protein structure where we have several other parts also, so little bit we should also know what is the protein structure, which is a large one and have a several molecular weights of 270 kilodalton. And apart from molybdenum atoms, so analytical part, that means the how many molybdenum center and what other part which is taking part in oxidation and reduction reaction, we should also know. So, it has two flavin molecules also, those flavin molecules bound as FAD, flavin adenine dinucleotide. Then two molybdenum atoms that we are seeing, that the molybdenum center which is responsible for the oxygen atom transfer, and 8 iron atoms bound per enzymatic unit. So, for the molybdenum center to work and show the enzymatic action on the xanthine molecule, what we see that the iron bearing centers, whenever we have some iron bearing centers like that of our ferredoxin or other related iron sulfur proteins, we will see that this particular iron center, when they settle between the two oxidation states commonly available for iron, that means the ferrous state and the ferric state, can give the electron to the molybdenum site at right potential, because we want to transfer, we want to move this molybdenum center from +4 to +5 and then to +6, because for the catalytic reaction these molybdenum centers are settling between +4 and +6 oxidation states. So, how we bind these molybdenum sites? So, in the within the protein structures, they are contained in molybdoterine cofactor and are active sites of the enzyme. So, that we have earlier seen that if we have two sulfur parts which are coming from molybdoterine part. So, basically these two sulfur groups are being utilized to bind this molybdenum site. So, this particular molybdoterine unit, so when this terine unit is bound to the molybdenum site, we consider it as a molybdoterine cofactor, and therefore, that molybdoterine cofactor is the active site of the enzyme. And what is the role of these iron atoms? So, iron atoms as part of 2 iron 2 sulfur ferredoxin type of thing, and therefore, this particular 2 iron ferredoxin or 4 iron ferredoxin. So, when we have certain ferredoxin molecules, so it can be 2 iron ferredoxin or 4 iron ferredoxin. So, when we have 2 iron 2 sulfur ferredoxin or 4 iron 4 sulfur ferredoxin, we all know that these 2 iron sites are in tetrahedral geometry, and you have these 2 sulfur and these 2, that means in all these cases this particular center is settling between Fe2 and Fe3. So, you can take out electron and you can put the electron to the system, but this one is giving much more electron, where you have a cube type of arrangement. So, we call is a cube like 4 iron ferredoxin molecule. So, this particular one, so alternate coordinates are occupied by iron atoms, and other 4 positions belongs to sulfur. So, this iron, again we have all iron in tetrahedral geometry. So, this particular geometry is important, and from that geometry it can give rise to these 2 oxidation states, iron 2 and iron 3. So, basically it can give off electron to the system where you have this molybdenum. So, this molybdenum you can have +4, +5 and +6. So, these are the electron pool basically. So, we are having some electron pool based on 2 iron 2 sulfur system or 4 iron 4 sulfur system, which is being donated to the molybdenum site and which can ultimately go for the corresponding oxygen transfer reaction. So, this is therefore a part of the iron sulfur cluster and they participate in electron transfer reactions. So, basically when we are talking about some reaction where electron transfer reactions are taking place, but some of these redox reactions are taking place based on FAD like NAD also and based on ferredoxin, which can be a good supplier of electron or which can take off electron from the system as and when required. So, if we see that what is happening there in the catalytic mechanism, the active site of xanthine oxidase is already you have seen is composed of the molybdoterinine unit with the molybdenum atom also coordinated to terminal oxygen, that means the oxo sulfur atom and a terminal hydroxide group. And interestingly, at this particular point it is important to note that if we have that molybdenum site which is bound to the oxo, which is bound to the double bond sulfur also, sulfoxide also, and then terminal hydroxide, because this particular terminal hydroxide function can generate very easily on the molybdenum center if we consider that molybdenum is there which is bound to our oxygen as well as sulfur and 2 sulfur from the pterine unit and bound to water molecule. So, in this pentacoordinated form, initially we have this water as the very useful ligand or very good ligand to bound to the molybdenum site, and this molybdenum site can have +4, +5 or +6 oxidation state. So, this particular one, so if it goes or if it bounds to the molybdenum in the highest possible oxidation state in this form, that means in the +6. So, you can think of that molybdenum 6 plus you can have, molybdenum 5 plus you can have and molybdenum 4 plus you can have. And we are talking about something where you have all these centers bound to water molecules, which is true for all other metal ions also. When we dissolve any typical metal salt in water, we always get a corresponding complex species like that of when we dissolve ferric chloride in water, we get the corresponding hexaaccoferric ion in +3 oxidation state. So, initially when nothing is available, so we have the loosely bound water molecule, it forms the coordinate bond to the molybdenum center. So, depending upon its transfer, that means how it is settling between this electron change, it can also consider the corresponding equilibrium related to the proton transfer, and these two transfers are simultaneously related to each other and they are engaged in some equilibrium which we consider as electroprotic equilibrium. So, this equilibrium will dictate that when a metal center in different oxidation states are bound to these water molecules, we can consider the corresponding pK values of the water, that means the free water which is not bound to anything. So, we all know the corresponding pK value of this water molecule, and when any one of these lone pair of electrons or both of them are utilized for the coordination to the metal center, we get something, and due to this donation to the metal center, this pKa value is changes and we are getting more and more acidic protons. So, pKa value is dropping down as we move from a oxidation state of +4 to +5 to +6. So, these water molecules, that means the hydrogen ions attached to the water molecules are more and more acidic as we go from a lower oxidation state to higher oxidation state. So, for that reason we get the corresponding information that this particular one, when pKa is lowering. So, this is the thing, that means the molybdenum in +6 oxidation state, it can immediately go for a proton loss such that you can have a corresponding molybdenum binding for OH and with the loss of one proton. So, instead of water bound to the molybdenum center, we have the hydroxide group bound to the molybdenum center. And this, if there is a reduction in the oxidation state, that means during this process if it goes down to +5 or +4 oxidation state, the pKa value of this OH group attached to the molybdenum center is further changed. Otherwise, it can go from here to a molybdenum oxo species. So, this particular one, so attachment of this water molecule to the molybdenum center is a very important attachment, and this ligand, after losing one proton, it can go to hydroxide function or it can go for to molybdenum dioxo species. So, that particular formation so very easily in water medium, when plenty of water is there surrounding the enzyme, surrounding the protein structure, it can go and attach to the molybdenum center, and depending upon its reactions of all these, so it can move to molybdenum oxo form, because whatever we are looking from here is that ultimately we can transfer this oxygen to the xanthine molecule for its corresponding hydroxylation reaction. So, either this oxygen or this oxygen from the water molecule will be utilized for hydroxylation reaction on the substrate molecule. Hydroxylation reaction on the substrate molecule. So, when our substrate is xanthine, which is be utilized for the formation of uric acid. So, what we get, we have to transfer one oxygen atom from molybdenum to xanthine, and in that process several intermediates are assumed or several intermediates are formed. So, the involved intermediates are very important to know the corresponding catalytic cycle, because if we are able to know what are the corresponding nature of these intermediates, then only we can have some idea that what type of transfer is taking place from molybdenum to the xanthine molecule, whether it is from the water molecule attached to the molybdenum center or already the dioxo function what is present on the molybdenum, that is getting transferred to the xanthine molecule. And in the intermediate form, which is very important for all the metalloenzymes, that whatever intermediates are formed there, if we can identify the nature of the molybdenum at the starting point, that means the catalyst at the resting state, if we know that, then only we can start thinking or start forming the entire catalytic cycle depending on the oxidation state of that particular transition metal ion. So, when we have the molybdenum, so immediately if the crystal structure for the corresponding metalloenzyme is available, we can know the corresponding environment, that means what are the donor atoms attached to the molybdenum and the corresponding oxidation state of the molybdenum. And during the transformation, how the molybdenum oxidation state is changing, and it is not always possible to identify the corresponding crystal structures for all the molybdenum center, that means the molybdenum in +6, +5 or +4 oxidation state, which can be crystallized and we can determine the corresponding X-ray structures based on those sites. So, we can take the help of the spectroscopic techniques. So, among the 3 oxidation states involved +6, +5 and +4, some of them, particularly the molybdenum 5, is well established as its corresponding EPR signals. So, EPR response, if we can monitor in the solution state the corresponding EPR response, and if we are able to detect the corresponding EPR pattern for the +5 oxidation state of molybdenum, we can think of that during this catalytic cycle molybdenum is getting reduced from +6 to +5 oxidation state, and in that particular process the molybdenum is also activating the oxygen atom for transfer to the xanthine molecule. So, during this transformation, whatever molybdenum center is active in the resting state, after the transfer of that oxygen atom which is already attached to the molybdenum site, and we are giving that particular oxygen to xanthine to produce the uric acid. So, you have the molybdenum center already there. So, that particular site will be vacant. So, if this water molecule is getting activated for hydroxylation reaction, and at the end when you have the transfer of this oxygen, say from this water molecule is taking place to xanthine molecule, we generate some vacancy over here. So, this will be vacant. So, to get back the original catalyst in the active site, so that means the regeneration. So, regeneration of the active site is possible through water coordination which is available in the system, and those water molecules. So, vacancy is created because this is transferred to the xanthine, and large number of water molecules are available in the enzyme surroundings, and that water immediately go and bind to the molybdenum site. So, this basically tells us that the reformation of the active molybdenum center which is catalytically active therefore occurs through the addition of water molecules which are available surrounding the enzyme system. That means, large number of water pool is there, and from that water molecules individually can go if one vacancy is created at the molybdenum site, because molybdenum, if it is stabilized in the pentacoordinated form, so it cannot be in a tetracoordinated form. Immediately the water will go and bind that particular vacant site and make that molybdenum center again pentacoordinated. So, in all these oxidoreductases, when we have some oxygen introduced to the molybdenum site and molybdenum dioxide form is forming and xanthine oxidase is generating. So, during the formation of this xanthine oxidase, we find that the molybdenum is getting activated through water coordination as molybdenum oxo compound, and that molybdenum oxo compound is transferring this oxygen to the xanthine molecule, giving xanthine oxidase. But in some cases we will know that this particular dioxygen is not involved like that of our iron bearing and copper bearing system, where iron is also bound to the dioxygen molecule and copper is also bound to the dioxygen molecule for the hydroxylation reaction. But this particular hydroxylation reaction is pretty interesting because it is only catalyzing through water molecule. So, water molecule is involved there and oxygen of the water molecule is incorporated on the molybdenum site, and that is ultimately transferred to the xanthine molecule. So, it is not that the dioxygen molecule is involved there for this particular hydroxylation. So, it is water mediated hydroxylation reaction based on the molybdenum enzyme on xanthine molecule. So, why we want to know this, that why these are so important. So, if we consider the corresponding the clinical biochemistry, what we know from the understanding that how much uric acid is forming in one person's body compared to the other, and when increases a particular level, we have several other things happening on this particular patient. So, clinical significance is therefore is important. In some cases, it is hydroxylating the substrate like xanthine, but in some other cases, it can also produce some superoxides also from dioxygen molecules. So, if the electron is transferred to dioxygen molecule itself, it is producing a superoxide. So, we can consider this as well a superoxide producing enzyme. So, they are found in serum and the lungs, and its activity is increased during influenza A infection. So, xanthine oxidase, so during some abnormal conditions in the flu, a person suffering from influenza A infection, the xanthine oxidase present in his or her body is little bit active. That means, this activity means if this is active, it can work well on the xanthine molecule, and xanthine oxidase is active and it is producing more and more uric acid. So, accumulation of the uric acid in the body would be more in some diseased condition. Also in some severe liver damage, so some cases when people suffering from a damage in the liver, xanthine oxidase is also released in the blood. So, a blood assay for xanthine oxidase can be utilized for the determination of the condition of the liver damage or some disease related to liver, which we also know that well known is the cirrhosis one, and the condition of the liver and how much damage has taken place on the liver related to the concentration of xanthine oxidase available in the blood, we can consider some information. So, in all these cases, whether our xanthine oxidase is little bit active more, or in some other cases where the liver is also getting influenced or getting damaged due to the presence of these xanthine oxidase, we want to do something to reduce the corresponding activity of this. So, this what is we are telling here is that its activity is increased. So, in some condition when the activity is increased, we have to slow down its activity such that we do not have that corresponding increase in concentration of the uric acid in the blood. So, some inhibitor which can go and bind to the xanthine oxidase system, that means it can go and bind to the molybdenum center, can function as a xanthine oxidase inhibitor. So, these inhibitors are nothing but which can inhibit the corresponding activity of any enzyme, which is a common terminology for all this inhibitor design. People can design as these inhibitors, so they are very good medicine also for reduce the activity of xanthine oxidase in our body. So, in a metabolic pathway, when we want to inhibit the corresponding action of xanthine oxidase on xanthine to reduce the formation of uric acid in our body, we use one such inhibitor which is known as allopurinol. So, which is utilized for the treatment of gout, because the gout is nothing but it is the corresponding manifestation of the large amount of accumulation of the corresponding uric acid, which is getting crystallized in the bone joints, which can give rise to severe pain to the patient. So, if we want to reduce the corresponding crystallization of uric acid, we want to reduce the corresponding concentration of uric acid, that means we should have such a condition where the activity of xanthine oxidase can be reduced. So, this reduction can be taken place by a suitable thing which is our allopurinol. So, this allopurinol, we will see what is that particular molecule. So, this allopurinol will be some molecule which will be related to the xanthine itself. So, this particular allopurinol will be acting on xanthine oxidase. So, because this xanthine oxidase is the target for the different drugs, So, this allopyranol will come and bind to this particular system, and the xanthine oxidase, instead of working on xanthine, because this xanthine oxidase can work on xanthine itself to get is oxidized to uric acid. So, it cannot work on xanthine, because instead of xanthine it can bind to allopyranol, and instead of oxidation of xanthine to uric acid, this allopyranol will be oxidized to something else related to the same type of reaction. So, if we know the entire structure of these, that means this is our allopyranol, and in this particular case the difference is this particular one part, that means in xanthine we have nitrogen over here and nitrogen over there, and this particular center was our carbon center. But in allopyranol these two nitrogens are adjacent nitrogen. So, it is again a diazine type of molecule on the 5-membered ring, but this particular part is basically related to when you have two adjacent nitrogen in any pentagonal or cyclic system, we know that this is our corresponding pyrazole part. So, it is very easy to synthesize. So, synthetic chemists know how to synthesize this particular part. So, this is basically pyrazole part, and in case of xanthine, when this nitrogen, these two nitrogens are non-adjacent, in between we can have a carbon, that is known as imidazole part. So, if this particular ring, that imidazole part is substituted by pyrazole part, this can function as a drug instead of functioning as a substrate for xanthine oxidase, and this xanthine oxidase can work on this particular drug as allopyranol, and this allopyranol is getting oxidized on this carbon now, giving us the oxypyranol. So, the product of this thing is that oxypyranol. So, it is a different course of reaction on the substrate molecule, and this allopyranol is therefore functioning as the corresponding inhibitor of xanthine oxidase. So, when we use this allopyranol as the corresponding drug for treatment of gout, we get a general class of different xanthine oxidase inhibitors. So, in general form, that which are the molecules which can go and bind to the molybdenum site of the xanthine oxidase, we see that a xanthine oxidase inhibitor is there, which will definitely go and bind to the molybdenum center and reduce the activity of xanthine oxidase. In our body, when it reduces the corresponding production of uric acid, and other medications that inhibit also the xanthine oxidase are indicated for treatment of hyperuricemia and related medical conditions including gout. So, gout as well as hyperuricemia, when the concentration of uric acid in urine is much more compared to the standard level, we know that the xanthine oxidase is much more active, and which is acting on the xanthine molecule, producing large amount of uric acid into the blood and ultimately to the urine. So, we design large number of inhibitors, and we can use this as their potency as a inhibitor, and which can also we can study or we can investigate for management of reperfusion injury, because in reperfusion injury also we can have the more active xanthine oxidases. So, we can have two different kinds of these purine analogues and the others. So, since we are talking about this corresponding oxidase activity on purine type of molecule, so some purine related molecules, because we do not want to change the entire skeleton which is our substrate much more, because otherwise if we can have a different skeleton compared to our purine molecule, we find that that particular thing cannot function as a very good or useful inhibitor, because it cannot go and bind to the molybdenum site easily. But little bit if we can modify, like that the formation of the allopyranol compared to our xanthine molecule, we see that the simple change, that means the carbon is changing to nitrogen and another carbon is nitrogen is getting changed to carbon. So, little bit modification of the parent substrate molecule can give rise to the design of the inhibitor molecules. So, one such analog of purine, which is our substrate, is allopyranol. Then what is forming from allopyranol, just what we have seen, that is our oxypyranol. So, this particular oxypyranol can also function as the inhibitor again. Because it has also several nitrogen donor points or donor groups. So, these nitrogen donor groups can easily go and bind to the molybdenum site, and it has still some position available which can go for hydroxylation. So, if the carbon atom is still available for hydroxylation reaction, we can go for another oxygen insertion, because already we have seen that during the production of uric acid we can have 3 oxygen atom on the entire molecule. Here also you can have the possibility of inserting the 3rd oxygen atom on the oxypyranol molecule. So, the second category is oxypyranol, then tishopurine is also another purine based molecule which can function as a very good inhibitor. So, these are the inhibitors which can work on this xanthine oxidase and can function as very good inhibitors. Then in the drug market is very huge, and other molecules are also people are testing, and the potency is also utilized, but they can be non-purine type of molecule. So, febuxostat and inositols, so they are corresponding other derivatives of inositols can also very useful to bind to the molybdenum site, such that it can protect that molybdenum site from binding to the xanthine molecule. So, this already we have seen this allopyranol. So, there are several other group of molecules. So, when we have the xanthine oxidase, we can react, basically is a very simple reaction what we can study, because whatever we are studying here is that particular molybdenum site which is there as the xanthine oxidase. So, molybdenum site is available, and that molybdenum site which is loosely bound to water molecule. So, that particular site is available. So, due to the displacement of this water molecule, we can put some different types of inhibitors such that the same molybdenum site is bound to the inhibitors. So, the binding position, so this nitrogens available on these molecules like allopyranol or oxypyranol is go and bind to the molybdenum site. So, different other groups, so in vitro study or in model animals like mice and rat, several flavonoids also which are coming from different fruits and vegetables. So, camphorol and myricetin and quercetin. So, these are from the biological origin like that of our fruits and vegetables. So, fruits and vegetable origin is also very useful to know, because sometimes we are consuming, because allopyranol is a synthetic molecule. If it is not available naturally, you can have to consume it as a drug. But these particular things, if we can study these, that these simple molecules from fruit origin or vegetable origin can go and also coordinate to the molybdenum site, and once they are coordinating, and if their binding constant is pretty high compared to the binding of the corresponding xanthine molecule, we can find that these particular molecules can inhibit the corresponding activity of the xanthine oxidase. So, they can function very well as some good and useful enzyme inhibitors. So, these and some other planar flavonones and flavonols. so flavones and flavonols with a 7-hydroxy group inhibits the corresponding xanthine oxidases. So, there are large number of molecules apart from the allopurinol is also available to function as some kind of corresponding inhibitor for xanthine oxidase. This is the corresponding structure. So, basic structure and basic skeleton for these molecules is that this is basically catechol type of molecule and we have several OH functions. So, this is not like allopurinol. So, chemoferol is such a molecule that we have several oxygen and OH groups. So, these are basically semiquinone type of fragment. So, when we have two adjacent oxygen atoms in a form where this particular function can behave as a chelation to the molybdenum side. So, its binding constant should be more, and this particular one when it binds to the molybdenum site, it very easily go and sit on the molybdenum site, and this particular molybdenum site on the xanthine oxidase will not be available to bind to the xanthine molecule. Therefore, this chemoferol can be useful as a very good xanthine oxidase inhibitor. And this particular molecule, which is of natural origin also, and large number of fruit materials, that means several plant sources are available, such as it can be available from tea, it is available from broccoli, witch hazel, grapefruit, cabbage, beans, endive, leek, tomato, strawberries, grapes, Brussels sprouts, apples and other plant sources. So, this is a very useful xanthine oxidase inhibitor. When we get all these from tomato and all these fruits which we take day to day, but it depends on the concentration, because since we are not consuming in the pure form as a drug, its concentration, that means it is bound in different form in all these food materials. So, this should be available to go and bind to the xanthine oxidase, then only it can inhibit the corresponding activity of xanthine oxidase, though they are very much available from the food material. So, the flavon or flavonol type of molecules, which we know is a plenty in all the food material, is a very good information that this can also function as a xanthine oxidase inhibitor. So, one such example of this inhibitor design tells us that if we just go for a corresponding xanthine oxidase, which is a very recent observation that people can go for, because this particular metalloenzyme site, which is molybdenum based metalloenzyme site, and sometimes it is very difficult to crystallize. That means, if we want to determine the corresponding crystal structure of this molybdenum site, so it is difficult sometimes to crystallize it in a good crystal, because it should diffract the corresponding X-ray diffraction. But another way of learning this particular form, that if we use some anion or some other groups, because whatever inhibitors we have discussed right now, that the corresponding pyrinol, allopurinol and this corresponding the different flavonols and flavones. So, those in the bound form to the molybdenum side is also difficult to crystallize, but if we can go for some inorganic oxo anion. So, inorganic oxo anion like that of your arsenite. So, if we go for crystallization of this particular species, where a arsenite anion has been taken, and this arsenite, where arsenic is present in the low oxidation state, not in 5 oxidation state, that means we have two combination of this arsenic based oxo anion. One is arsenite, another is arsenate. So, this particular arsenite, so simply reacting this corresponding xanthine oxidase. So, if we have xanthine oxidase and if we are trying something where we have SO3, which is 3, that means 3 minus, and we are not using any species which is related to arsenate. So, arsenite will be there. So, between these arsenate and arsenite, we have a separation from this one particular oxygen atom. This can also produce some other species which is also arsenite based, which is SO2 minus. So, in solution, any of these two species which is based on arsenic 3 oxidation state compared to arsenic 5. So, they are different arsenite species, and basically what we are doing a very simple inorganic chemistry or coordination chemistry at this particular point. So, that we are taking the help of typical coordination chemistry. What we can do is basically the crystallization. Since we are having this xanthine oxidase, which is, say, if we consider is a molybdenum 6 species, we have the ligands from the pterine part, we have the oxoform and all other thing. Still we can have from this coordination sphere, we can have some charge. So, if we have a cationic charge on it, +1 or +2 or +3, so we can have different cationic charges on the protein envelope or the enzyme envelope. So, definitely during crystallization it will definitely go for attracting the corresponding anions. So, if arsenite is utilized, it can go for corresponding crystallization because you can have the charge neutralization. The way we go for the typical crystallization, that means if we have simple Fe hexa iron 3 in cationic form. So, we can supply some anion such that we get some molecule which is electroneutral. So, the electroneutrality will definitely tell us something, that when we go for electroneutrality, because you have the medium as the aqueous medium or water based medium. So, if we are able to neutralize the positive charge accumulation on the protein surface or the enzyme surface by some anions, providing suitable amount of anionic charge, we are reducing the corresponding cationic charge accumulation on the protein surface. So, the corresponding tendency for crystallization would be much more, and at the same time these oxo anions. So, these are typically different oxo anions which are arsenite based. So, these arsenite based oxo anions can have another tendency, not only bind to the corresponding protein or enzyme surface, because on the surface we have some cationic species like the nitrogen based deuterions and all these, but it straight can go inside and can approach to the center where you can have the molybdenum. So, what we can think of, that this particular thing is well known, that it is responsible for the hydroxylation reaction of sp2 hybridized carbon center, not sp3 hybridized. So, it can go for the corresponding hydroxylation on the sp2 hybridized carbon center on xanthine. It can go for the corresponding phenol type of thing, but it is not going for the methanol which is sp3 hybridized. So, what we get, that during the reaction of this arsenite thing, we get a mu sulfido mu oxo double bridge. So, already we can have these terminal groups, already we know that molybdenum oxo and molybdenum sulfido groups are present, and this was basically our water molecule. If we recall the corresponding active site of the enzyme, this was our water molecule, this is the corresponding oxo and this is the corresponding sulfur system. So, if we just simply attach it with that of your arsenite based on ASO2, which is coming from ASO3 species. So, we get something, because this arsenite already this oxygen is present to this particular oxygen is present with this arsenic. So, it will immediately remove the water loosely bound to the molybdenum site, and it establishes new bond which is from this oxygen of the arsenite to the molybdenum site. And this arsenic also has some tremendous tendency to bind to the sulfur also. So, at the same time it can also bind to the sulfur, because the arsenic has affinity for binding or coordinating to both oxygen and sulfur. So, basically it can establish a doubly bridged arrangement. So, it is basically a system where we have based on that metalloenzyme, but is a molybdenum arsenic dimeric form. So, that dimeric form what we are getting that due to the establishment of molybdenum and arsenic between these two. And this is one particular form, and this is what we have seen in the other form. That means, when we have this water also here, this water can go for deprotonation, and arsenic when approaching the molybdenum site, it can either go through this sulfur or go through this oxygen. So, if we establish the first thing, that means if we can go to sulfur, it can in the next step it can bind through this oxygen through the removal of one water molecule. So, this catalytically essential sulfur is there, and high affinity of reduced xanthine oxidase reductase for arsenate. So, what we see that for this particular reaction, the molybdenum center what is present, this particular molybdenum center is useful or required, but not that molybdenum, but also the sulfur center is also useful, because the catalytic function is dependent on the presence of the sulfur. But when we are trying to block this particular reactivity of molybdenum as well as the molybdenum sulfur assembly through the attachment of the arsenite group attached to that, what we see that we just basically block the particular site in this form. That means, this oxygen is also not available for binding to the xanthine molecule, and we are blocking this particular assembly. So, arsenite is definitely therefore a very good inhibitor, and if we can consider that this oxygen is available and this oxygen is responsible for transferring to the xanthine molecule. So, what is the role of this sulfur? That people have earlier established that when the presence of first this oxo group and the sulfido group on the molybdenum site was established, this has been established through the removal of this sulfur group from the molybdenum site by doing a very simple reaction. That means, if we have MOS, how we can establish this MOS function from this particular site, we just simply react it with this particular cyanide ion. So, any form of this cyanide in form of sodium cyanide or potassium cyanide in solution, it can very easily remove thiocyanate anion from the system. So, thiocyanate groups are removed from this system, which is basically removing this particular sulfur function from the molybdenum, and when this is getting deactivated through the removal of thiocyanate from the molybdenum site, we see that the corresponding catalytic activity is also changing, and that catalytic activity reduction will also tell us that the presence of this sulfur was important for the corresponding action of that xanthine oxidase. So, this particular sulfur is therefore important to be a part of this activity related to the molybdenum site, and this we see that this can inhibit the xanthine oxidase. Particularly, it is binding in the reduced form of the enzyme, and this very good account you can find from a journal page or the Journal of Biological Chemistry. So, this basically tells us that the structural basis of the enzyme, that means whether MOOH ligand that initiates the nucleophilic attack on the substrate molecule or the MOS moiety that serve as the hydride acceptor during the course of the reaction, that we will see that between these two things, that means when we have the molybdenum function attached to the water molecule and molybdenum function attached to the sulfur unit, what type of nucleophilic attack we can think of on the substrate molecule. So, the positioning of these two groups, that means whether this particular MOOH bond is present in the equatorial side or the axial side is important. That means the availability of the MOOH ligand from the equatorial side, which is important. That means it is not operating from the axial side for the nucleophilic attack. That means MOOH is attacking on the xanthine molecule for the hydroxylation reaction, and the MOS moiety that is basically serving as a hydride acceptor during the course of the reaction. So, this particular MOS group, which is when it is taking up the hydride ion, so it is going from MO double bond S to MOSH. So, during that part also, when it is functioning as hydride acceptor, so this cannot function as a nucleophile to attack on the substrate molecule, but this particular MOOH function can be a very good nucleophile, and this MOOH which is originating from the water molecule and that ultimately delivering this particular oxygen atom to the substrate xanthine molecule is important to know the corresponding pathway for the catalytic reaction. So, we will continue this particular part also, because the arsenic inhibited form, which is a 4 coordinated one, and in a typical geometry in the oxidized form, and the 3 coordinated form is also in the trigonal planar geometry in the reduced complex. So, what are there basically in the form, that means this is the trigonal one and this is another type of binding. So, what these two form, that means the 4 coordinated form between trigonal pyramidal geometry and the tri-coordinated form with the distorted trigonal planar geometry in the reduced form, because these two types of geometry around arsenic are also important, because we all know that the geometry is important for stabilizing a particular oxidation state. Okay, thank you.